Okay, today we're going to go into a really important topic called simplifying radicals. Radical expression is a vocab term, right? It means something that has that square root symbol. And I just want to talk about the difference real quick between radical and square root. So radical is the symbol, and then the square root is the number that you're like taking the radical of. So like number in the symbol, right? So they can use sort of interchangeably. When I say radical, you should know that there's a square root symbol, but you should also know how to simplify something in a square root. Like for example, if you see the square root of 25, you should know that that is 5. Or if you see the square root of x squared, you should know that that is x, right? Actually, there's two answers. This is in the vocab too. Square root of 25 is 5 and negative 5. Square root of x squared is x and negative x. Because if you were to go back and multiply them, right, 5 squared equals 25 and negative 5 squared equals 25 because the negatives cancel. So you want to be able to move interchangeably between those. Okay, so let's do a few examples in the notes. We have 36. 64 and 40. Okay, so sort of like before, if I see this, I know that it's a perfect square. I don't know if perfect square is a vocab word, but it will be. So 36 is a perfect square. That means two numbers can be multiplied to make it. It's 6 times 6. So we know the square root of 36 is 6. Similarly, the square root of 64 is 8. And then this one's a little trickier because it's not a perfect square. So if we think about it, 6 squared equals 36, and 7 squared equals 49. So it's somewhere between 6 and 7, right? So if we look in our calculator, square root of 40, 6.325. Calc. But this is good just to know what it's between, and then we're actually going to do something. So we're going to use the product property of radicals. So it's this rule right here where the square root of a times b equals the square root of a times the square root of b. So since you have this radical symbol, you can break up what's inside of it. So if we were to take our problem here, right, I'm going to just highlight this because it's really important. Right? So if we have the square root of 40, we could break it down into the square root of 4 times the square root of 10. So I'm going to go into more detail with that later. But let's use this number line. So we will use the product property with our trusty perfect squares number line. So here is a number line. It just shows, you know, if I'm trying to figure out square root of 101, I know it's between 10 and 11. And a way to make this line is these 4 steps. But I'm actually going to go through some problems first and then come back so that we can sort of contextualize like why we're doing the number line. Okay, so there's 2 methods to simplifying radical expressions. So the first method is going to be this method using the number line. The second method, finding factors. You can use a factor tree. Okay, so we're going to do method 2 and then we're going to do method 1. So for this one, when we want to simplify this, we're going to take 12 and we're going to find all the factors. So we can do 2 and 6, and then we have 2 and 3. So essentially, when we're simplifying radical expressions, if you can find 2 of a kind, you're allowed to pull it outside of the radical, right? So think about like all these numbers I trapped inside the radical, but if you can find a buddy, you're allowed to leave. Right? So using the product property from above, we could rewrite this as 2 times 2 times 3, right? Or we could write it as 2 times 2 times 3. So both of these ways work. What you want to notice is since there's 2 of these here, they're allowed to escape. So we're going to go 2 root 3. Another way is like, okay, since I broke this down into here, you can see square root of 2 times the square root of 2 just becomes 2. Because if you have the square root of two things next, like times each other, right? Imagine square root of 25 times the square root of 25. So we know that this is 5, and we know that this is 5, so we know that that is 25. So when you have two things in a square root times each other, they just equal what's inside that square root. So this is using the number tree, right? We see that we have the two 2's and we pull it out, or you can break it up. This is the same thing, right? Using the product property of radicals. We know this is the same thing. So this is our simplified version, right? So I like to use the number tree to help visualize like, oh, I have these two 2's, I'm going to pull it out. Okay, let's try 98. So sometimes you want to use a calculator to help. Sometimes you get used to it and you can see it right away. So I know 98 is divisible by 2 and 49, and that's 7 and 7. So I see right now that these two 7's can be pulled out, and it'll be 7 root 2. But if you wanted to, you could sort of write it out longer to see it. And we could do 7 times 7 times 2, 7 times 7 times 2, root 7 times root 7 times root 2. And then these two become 7 root 2. Okay, and let's look at 200. So 2 and 100, 2 and 50, 2 and 25, 5 and 5. Okay, so if we see here, we have 3 2's and 2 5's. So we can pull out a 2, we can pull out a 5, and then whatever's left inside is a 2. And then there's this rule. Let me put it on the side, sort of like a reminder. When multiplying radicals, you can multiply outsides together and insides together. So I should probably make this a vocab term if I haven't already. Here's an example, right? 2 root 4 times, no, that's not a good one because root 4 is 2. 2 root 3 times 4 root 7 would be 8 root 21. So whatever's on the outside has to stay on the outside. Whatever's on the inside has to stay on the inside. If you can then simplify this and pull stuff to the outside, you can. But this is the rule for multiplying radicals. Right? So if we go back to our example, we have 2 times 5 root 2. So this is all on the outside. So this would become 10 root 2. Right? If you wanted to rewrite it, you could do root 2 times root 2 times root 2 times root 5 times root 5. We see this becomes a 2, this becomes a 5, and then we can simplify to 10 root 2. So this is the way to do it with like finding factors using a factor tree. The other way is using the number line. So I didn't leave that much room, so let me try it over here. 12, 98, 200. Okay, so what you want to do is you want to look at these and you want to try and figure out which of the perfect squares will go into it, right? So if I'm at root 12 and I'm going to look at this number line and I'm going to see which of these numbers will go into 12, right? So I already don't want to start here because that's too big. So is 12 divisible by 9? No. Is 12 divisible by 4? Yes. So I can do root 4 times 3. And then I know that this 4 becomes a 2. So then I do 2 root 3. Right? Let's try 98. So 98, we'll start here at 100. It's not divisible, yes, divisible, right? I could do 98. So I do 49 times 2, and then I know that this turns into a 7, so I do 7 root 2. And then 200, If we look here, we can see this 100, right? So we go 100 times root 2, and then I do 10 root 2. So this one can sometimes take a little bit longer because you're breaking down each step. This one, you'll have to really start to recognize these perfect squares. But it's the same idea. It's just whatever method you prefer. So I'm going to go through and give you steps on how to find this number line. So the first step is to write a list of perfect squares. Start at the number given in the problem. So like, for example, this was 12. We're going to check each perfect square on the top of the number line until you find a factor of the given number. Write that number first under a radical, right? So we found 12. We found that 4 went into it, so we wrote square root of 4. Write the other factor second under a radical. So for this one, I didn't times it like that. Like this one, they wrote it like root 4, root 3, like that. Simplify the first factor. Because it's a perfect square, it will always simplify to a whole number. So if I was to go through these steps one at a time, right, let's do number 2. So I write my list of perfect squares. I checked, let's do root 98. I checked the 49, and they said write that number under the first radical. Write the other factor under a second radical, and then simplify the first one, and it's going to simplify to a whole number. So again, use either of the methods. All I want is that you simplify it correctly, because simplification for me is what I always want. I never want to see this. I always want to see this, right? Same thing with fractions. Same thing when I have like a 4 over 1, I want to see it as a 4. So it's the same idea. All right, let's look at some examples and then we are done. So I'm going to do the perfect square method. And then maybe I can do the other method down here. Okay, so we have, you can stop and pause the video and then come back and check. That's what I would recommend. But if you need to watch, that's okay. Okay, so we have a -4 times the square root. So I know that this is divisible by 300. I mean, I can pull up the line right here so that we have it available. So let me just fold it. Right, here's my number line. Okay, so I know that 300 is divisible by 100, so I'm going to write 100 times root 3. This becomes 10. There's a little multiplication symbol there. Whenever there's a number in front of a radical, it's really times that. So -4 times 10 times root 3, -40 root 3. All right, 2, I know this is divisible by 9. And then this simplifies to 3. And then this simplifies to 6. 10, 108 is divisible by 9. I think it's 12, right? Whoops, 108 divided by 9. 12. So, but if we look, this can be divisible by even more. So I actually didn't pick the biggest factor. If we look here, right? 10, 9, 4, 3. So 10 times 3 times 2 times root 3. So 30 times 2 is 60 root 3. So what I actually could have done here is I could have done 10, 36, 3. But I didn't see the 36 right away. I only saw the 9. But it still simplifies to the same thing. All right, for 7, there's nothing, right? 33 doesn't fit into any of them. It's only divisible by 3 and 11, so it's just 33. This one, we have the -1 in front, right? We're going to times that by 100 times 100. You might be able to, wait, no, it's not times 100, it's times 10. So then negative 1 times 10 times root 10, that becomes negative 10 root 10. Just be careful with the signs, right? This negative's on the outside. You're not allowed to have a negative on the inside. That would be an imaginary number, and we haven't gone over that. All right, so we have negative 1 times root 26 is divisible by, what is it divisible by? I think none of these, right? Let's do a tree just to check. Right? That's not anything, so it's just going to be negative root 26. Okay, so if you like that method, you can stop there. Otherwise, I'll do them again with the tree method. So we have negative 4, 300, 2, root 18, 10, root 108, root 33, negative. Okay, so this might take longer, but it's a little more intuitive for some people. Okay, so for 300, we have 3 and 100. We have 2 and 50. We have 2 and 25, and then we have 5 and 5. So we know we can pull out a 2 and a 5. So we have negative 4 times 2 times 5 root 3. Negative 20 times 2 is negative 40 root 3. Right, same thing. Okay, for 18, we have 2 and 9, which is 3 and 3. So we have this pair here. We're going to pull out a 3. We have the 2 already, so 2 times 3 times the root 2, 6 root 2. All right, same thing. Here we have 108, 2, 54, 2, 27, 3, and 9, 3, and 3. So we could pull out a 2 and a 3. 2 times 3 is 6, so we could do 10 times 6 times root 3, 60 root 3. 33, right? It becomes 3 and 11, so there's nothing there, so we just keep it as 33. 1,000, 10, 100, 10, 10. So we could keep going. We could do like the 2, 5, 2, 5. But this one we know we can already pull out. So we could just do like 2 and 5. So we have negative 1 times 10. That's what I pulled out there. Times root 2 times root 5. That becomes negative 10 root 10. And then finally here, we already did the number tree up here, right? 2 and 13. There's no pairs, so it's just going to say negative. So when you're doing the factors, just make sure you don't forget the negative sign, right? Because here we factored out 1,000, positive 1,000, but we have to make sure you remember, like, the original problem was saying negative square root of whatever that was. So always be careful with your signs, because you're going to get it wrong if you mess them up. Even though it seems like you're close, a negative number compared to a positive number is very different.